Hello, in this video I'm going to talk about stellar fusion and take a look at the main processes, the nuclear processes that are occurring inside the cores of stars. So this is the central part of everything that's happening in stars. It's what's providing the energy to make them so hot. It's what's also providing the energy and the outwards radiation pressure and forces that's stopping a star from continuing to collapse under gravity. So, this is what stars all are about. So we need to know what these fusion processes are. Now, there isn't just one fusion process that happens in all stars, but there are certainly dominant processes which occur far more commonly than other processes. So that's what I'm going to go through here, in particular the proton-proton chain and the CNO cycle. So these are the two main ways that hydrogen gets converted into helium inside the core of stars. So let's start then with the proton-proton chain. And when we're talking about protons, essentially we are talking about hydrogen. This is just ionized hydrogen. So we're starting off with some protons and we're going to turn that into helium. And this is the most dominant process in smaller stars, lower mass stars. So stars like the sun, anything which has got less than sort of maybe 1.3 solar masses. So if you've got stars that are that sort of size, so fairly average to light, then proton-proton chain is going to dominate. In the sun, you're looking at about 99% of the energy is coming from proton-proton chain. So in this, we've got a first couple of steps that need to be performed twice. So we've got two protons get added together in order to create some deuterium, a positron, and an electron neutrino. Now, just to go back to our particle physics on all of this, you can see that looking at all of our quantum numbers and such like that we've got on all this. So you can see just that adding the two protons to get deuterium, we've gone from two protons to a proton and a neutron. So that's pointing at the involvement of the weak interaction, because we got a proton going to a neutron. So we've got a flavor change on a quark, which means that must be the weak interaction that's involved. That's why we're getting an electron neutrino coming out as one of the products of this. Obviously, we need the positron in order to make all the numbers add up on this. So adding up top and bottom, we've got two on either side, two at the top, two at the bottom. And then the weak interaction is what's involved, and that's what's giving us an electron neutrino. Right, once we produce this deuterium, we then add another proton to the deuterium. So the deuterium plus the proton, that's then going to go to some helium-3. This time you can see we haven't got a change in the numbers of protons and neutrons. Yeah, we've started here on the left-hand side with two protons, one neutron, and that's exactly the same as we have in the helium-3. So there's no weak interaction involved in this. It's an electromagnetic interaction. So we get the release of a photon. Now these two steps release some energy. We get 2.2 mega electron volts for this first step, for zero binding energy for these protons, and then we're binding them to deuterium. So this is talking about the binding energy here at a deuterium. Now some of that energy is going to be going to the neutrino, obviously, but still we're producing a little bit of energy there. Some of it's going to go into the kinetic energies of the other products. Then for this second step, we're getting a bit more energy. We're getting 5.5 mega electron volts. So that's some energy that's going into photons, again, with some in the kinetic energy of the helium-3. But we got some release there, and we've got helium-3, but we want to end up with helium-4. That's the end point of this process. Now, if this is done twice, these steps here, so we get 2 times this, means we've then got 2 helium-3 nuclei. These then add together in the final step of the proton-proton chain. So we've got a helium-3 plus a helium-3. That then goes to our helium-4, plus we get 2 protons back. which, you can see that as being 2 of the protons we started with, really. And again, adding up all of these, we've started off with, on the left-hand side, 4 protons, 2 neutrons, and we've got 4 protons, 2 neutrons again. So this is another electromagnetic interaction, get another photon release. This time, it's the big one, 12.9 mega electron volts. But of course, we are doing the first 2 steps twice. So by the time you've added those up twice, in total for this whole thing, we're getting 26.7 thereabouts mega electron volts by the time we've done the whole process. We're getting a bit more because the positron here, that's going to annihilate with an electron. So this positron that we're getting at this stage, the first step of the proton-proton chain, that'll annihilate with the multitude of electrons that are kicking around in the core of a star. That will just turn into a photon, releasing another couple of mega electron volts. So we end up with this 26.7 mega electron volt release of energy. Now, a lot of that is in photons, some of it's in the kinetic energy of the other products, some of it is taken away by these 2 neutrinos, because remember we're doing this first step twice. And these neutrinos, they don't really interact with anything in particular, they just pass straight out of the star. They're very elusive particles, neutrinos, so they don't do anything to support the star against gravitational collapse, but the rest of the energy will be. Of course, the kinetic energy that's going into the other fusion products, that's adding energy to the plasma. And also you've got the energy in the photons. I mean, the photons are going to interact with protons, electrons, and things like that. I mean, all of this is going to heating the interior and keeping the star stable, stopping the collapse. So this is what's going on inside these smaller stars. When we get to heavier stars, we get up to more massive stars that have gone above this, about 1.3 solar masses, then we've got higher temperature, we've got this higher mass, and then you get the CNO cycle. Now the CNO cycle has got a few more steps in it, but it's achieving the same thing. I mean, we're taking protons and we're combining them together to produce helium-4. So it's the same thing going on. There's also more than one route through the CNO cycle, but I'm going to go through the most common one, the one that gets included in most of the textbooks. And the CNO in the name here, this is referring to carbon, nitrogen and oxygen, which act as catalysts at various stages in the cycle. So that means that they're used throughout the CNO cycle in order to help the nuclear reactions take place. But once we've got to the end of the cycle, no change has actually happened to the carbon, nitrogen and oxygen. Right, if you're going to draw, write out one equation covering the whole CNO cycle of what goes in at the beginning and what comes out right at the end, then you don't need the carbon, the nitrogen or the oxygen in that equation. That would just be an equation of combining protons to form helium-4. So the carbon, nitrogen and oxygen are just catalysts, as we're going to see. So let's go through the 6 steps of the CNO cycle then. So we start off with our carbon-12 and a proton. So these combine, we're going to get some nitrogen-13. And again, you can see, looking at these numbers, the numbers of protons and neutrons haven't changed. This is an electromagnetic interaction, so we get a photon coming out with 1.95 mega electron volts. So the carbon has changed, but like I say, this is only in the midst of the cycle. When we get to the end, we'll see this carbon-12 comes back again, and we end up back where we started on that front. Now the nitrogen is unstable, so that is going to decay down to carbon-13. So we can see this is a weak interaction for all of the reasons I've been through before. We've got a change in the numbers of protons and neutrons. So we get a positron come out and the electron neutrino that goes with those weak interactions. And that releases 1.2 mega electron volts. This is just beta plus decay. This has got a half-life of about 10 minutes thereabouts, so it's fairly quick beta plus decay, especially as this is going on loads. So you're going to be getting a lot of this decay going on because there are so many CNO cycles happening in a star. Then now we've got this carbon-13. That carbon-13 is going to combine with a proton, which is then giving us nitrogen-14. That gives us a photon. That gives us 7.54 mega electron volts. So we're ramping up a bit there. Now we've got nitrogen-14. That combines with another proton, giving us some oxygen-15 and a photon, giving us 7.35 MeV. The oxygen-15 is unstable, so that is going to decay, beta plus decay again, giving us nitrogen-15, our positron, and the electron neutrino, and 1.73 MeV. And then the last step is combining, that 15's gone a bit wonky, so the nitrogen-15, add in the fourth proton. So you can see we've now had 4 protons go in, and we go back to our carbon-12 plus the helium-4, and you get another 4.96 MeV on that last step. So we've got these 6 steps. 2 of them are beta plus decays. The others are, just combining these protons in. So we're adding in a proton here, a proton here, proton here, proton here. That's our 4 protons in, and we've ended up with our helium-4, and the carbon-12 has come back again. We've got 2 positrons that have come out in the same way as we had 2 positrons in the proton-proton chain. Remember, we're doing this first step twice here. So those 2 positrons will annihilate with electrons, give us the photons from those, and we end up with the same. We're getting this 26.7 MeV again when you add it all up, because we've done the same thing. Whatever path we take with the conservation of energy, both of these, whether it's proton-proton chain or the CNO cycle, we've taken 4 protons and bound them together into helium-4. So whatever energy release we're going to get is going to be the same in both cases. So you get this 26.7 MeV, whichever way you're going about it. The reasons behind why one of these processes is going to be dominant over the other. You've got, the temperature is certainly a crucial factor in this. If you're combining 2 protons together, okay, they're both positively charged, but they're not as positively charged as trying to get a proton onto a carbon-12 nucleus where you've got 6 protons there. So that's certainly an issue. You've got the abundance of carbon as well. Some stars have got more carbon than others, so you need to have some of that around for it to have a significant effect and start catalyzing the CNO cycle. And then you've got various things to do with cross sections of these different particles, getting into the details of particle physics, plasma physics and such like, and the probabilities of them interacting. But there's certainly a case that the CNO cycle, as I said, does start to dominate for those higher mass stars. And you get other processes that can come into play for even hotter, even higher mass stars, higher temperatures. Then you can get things like the triple alpha process. So for triple alpha, and it is what it says, we've got 3 alpha particles, so 3 helium-4 nuclei, which are going to combine to produce some carbon. So if you add 2 of them together, you're going to get some beryllium, because we're then going to be up to the 4th element in the periodic table when we've got those 4 protons there. So you're going from helium, you're then going up to beryllium. When you've added 2 of them, you add another one in, and we're going to get some carbon. So these 3 helium-4s are going to give us a carbon-12. Sometimes you'll even get another one going up to oxygen-16. But again, you need higher temperatures to make this happen. You're getting more repulsion in these nuclei, and of course you need to have synthesized a lot of these heavy elements in order for it to happen. So yeah, there's a whole range of things that can go on inside the cores of stars. But proton-proton chain and the CNO cycle are the two that you certainly want to start with. And they're not that hard to remember, really. Okay, you don't have to worry about all the details, really, of the MEVs. You can just get a ballpark idea with the energies. So say you were going to start learning the proton-proton chain. Well, first of all, get used to fairly easy steps, really. I think this one's easier to remember. Yeah, we're adding 2 protons at the start. I mean, what else are you going to do? So 2 protons to deuterium. If you know your what's going on with your particle physics, then this has to be the other pair of products, the positron and the electron neutrino. Then we're just adding in another proton. You know, again, it's all just there in the numbers when you add in that. Do it twice and add the 2 heliums together. So just make sure, if you understand the steps, you know, why are we getting the neutrino there, why are we getting the photon there, then it's quite easy to pull this together. And then you can also see that we're more or less getting half and half the energy. Okay, it's not exactly that, but we're getting about half of it by doing these first 2 steps twice, and then we're getting the other half in the combination of the helium-3s. With a CNO cycle, I find it easier to remember the 6 steps in these 2 blocks of 3, because if you're in these 2 blocks of 3, you can see that the middle one of each block is where we've got the beta plus decay. So we're doing add a proton, then a decay, add a proton, and then we're doing add a proton, decay, add a proton. So that certainly helps to fill in what's happening, because you know that we're getting photons coming out everywhere else. It's just in these middle ones where we're getting our beta plus decays. Similarly, it's quite easy to remember the steps where you're getting most of the energy. So it's the 2 in the middle, it's the 3rd one and the 4th one. So thinking of it as these 2 blocks of 3 where we've got beta plus in the middle of each one, and then it's the 2 in the middle that are giving the most energy, then you're most of the way there for having a structure for remembering that CNO cycle. Because there's not too far you can go wrong when you're adding in these protons. You can see, particularly for the first 3 you're putting in, you're taking carbon up from, so it's going from 12.6 to 13.7. Then when we're doing it again, we're going 13.6 to 14.7, and then the 3rd proton 14.7 to 15.8. So you are just stepping the numbers up. These aren't complicated little nuclear equations that we're writing out here. Okay, the last one's a bit different, but you know the helium's got to drop out. So if the helium has got to drop out, okay, you are taking the 15.7 of nitrogen, making it a 16.8, but then you're just splitting that into what you started with a carbon and your helium-4. So it's quite easy to get into a system, I think, for remembering these. So it's worth just trying to write these out a couple of times, try and fit that system to when you're writing them out. And within half hour, you'll just be writing these out without really thinking about it. So there you go. That's a quick overview of the basics of stellar fusion and the 2 main ways that stars are producing energy.